Richter numbers are often used to measure the strength of earthquakes, or as in this case, tsunamis, and they are an example of a logarithmic application. And the formulas given here are the Richter number is equal to the log of the ratio I divided by I0, where I0 is a reference intensity. And we'll generally refer to I0 as the smallest intensity that can be measured by the seismic equipment. But depending on the context of the problem, you might use a different value. So we can use the difference of these Richter numbers to construct our log equation. So the actual Richter number at 9.1, we can then subtract from that the estimated Richter number of 8.0. And each of these numbers, again, is going to be represented as the log of a ratio. So this is going to represent log of, in this case, the ratio between the actual, so I'm going to put intensity A for actual, divided by I0, the reference intensity measured by the equipment. And then I'm going to subtract off the log of the estimated intensity, or IE, divided by, again, the reference intensity, I0. On the left, we have a difference of 1.1. And on the right, we can combine these two log terms. And since the separated terms are subtracted, what we're going to do with the insides is to make this a ratio, because the subtraction means that we will divide by the interior here. So we'll make this a complex fraction, IA divided by I0, and this whole thing will be divided by the second fraction, IE divided by I0. And if we simplify this, we take the first fraction, and now we're going to multiply by the reciprocal of the second fraction, which is, in this case, I0 divided by IE. And as you can see, these I0 terms will cancel out, and so we're left with the simpler fraction of just log of IA divided by IE. So putting the parts of this equation together, we get 1.1 on the left is equal to the log of this ratio, log of IA divided by IE. Now, if you take a look at the question, it asks how many times greater was the actual wave than the estimated wave. And so this how many times greater is this ratio, IA divided by IE. So the only thing we need to do now is to isolate this ratio, IA divided by IE. And one way we can do this is to convert this log equation into an exponential equation. And remember that common log has a base of 10. So if we rewrite this, again, as an exponential equation, we can take the base, which is 10, raised to the power, which is in this case 1.1, and that's going to equal the argument, or the interior of the log, which is the ratio IA divided by IE. And when we calculate 10 raised to the power 1.1, that comes out to be about 12 and a half times. And so what that tells us is that the actual tsunami, compared with the estimated value, was 12 and a half times greater. And that's a pretty large difference in order of magnitude. And when we look at the numbers 9.1 compared with 8.0, we don't really get a sense of this difference of 1.1 being an enormous difference. But again, we can see that a factor of 12 and a half is significantly greater.